Good afternoon, everybody. So let's go ahead and jump right in and get started. The webinar will attempt to give you some ideas and methods for improving edge quality on parts coming off your punch presses. So today we're going to be taking a look at a number of these bullet points. Burr is probably going to be the biggest thing most people battle with in terms of edge quality, but there's some other areas as well we'll discuss. And how to get rid of, or at least control, most of the burr many times relates to some of these other bullet points. So when to sharpen the tools, using proper die clearances, machine alignment, pinch points we'll go over, maybe some ways to minimize those, possibly even eliminate them, nibble marks, and then maybe introduce some alternative methods to improving edge quality with some of these tools, which we are calling the wheel family, either scoring or shearing, so forth. So first off, what is a burr and where do they occur? Most of the time this is pretty obvious, but we will introduce some methods to help kind of minimize, or some tooling methods to help smooth these over if you've done the best job you can and you're still getting an unacceptable burr. So, some basic things real quick we'll go over, and how to address these and troubleshoot a little bit. So the creation of a burr on a punched part. Pretty obvious, as you punch a hole or slit or use your parting tools, you're going to get somewhat of a burr. And how do we control this, and why is it created? So we're going to take a look at a punch process. Basically, this is going to be a slow motion video of a piece of metal being punched. It's actually kind of a super slow-mo video, kind of like watching a bullet pierce through the metal on Mythbusters, if you've ever seen that. It's a pretty cool little video. So I'm probably going to run it through twice. It's in slow motion, obviously, as I mentioned. The second time we'll go through it and I'll point a couple of things out. So let's take a look at this here to start out with. So pretty interesting, I think, watching the physics of a hole being created along with the burr that we're sort of focusing on. A couple things I want to point out, just to rewatch this as I pause it, which will kind of relate to doing some troubleshooting down the line. If we kind of understand where and how the burr is being created, we can at least address how to eliminate or at least minimize it. So watch this thing again. And right here you can kind of see the punch just contacting the top of the work surface or the sheet of material you're punching. And you can see the little depression starting. We go a little bit further, you can just start to see that fracture, and then basically the slug breaks through, and then distorts the slug face a little bit, so you get kind of a little bit of a dome shape to it, and eventually that slug, once the fracture line is complete, will pop through and obviously travel down through the die opening. At least that's the way we hope it works. Okay, so back to the PowerPoint here. So what we end up with after the hole has been punched is sort of depicted in this cross-sectional view. On the very top, you can see the punch hitting the sheet, kind of mimicking a little bit what you just saw in that video clip. If you pay attention a little bit to the middle section here, there's a number of things going on. You can look at and see the description and the labeling. Now, we've got a bunch of things going on here. You know, why should we bother to be even interested in all this? Well, mainly it's so we can understand and try and minimize the burr that I mentioned, but it helps troubleshooting. If you know how and where these burrs come from and what some of the other features are on this little depiction of a punched hole, we can kind of address these things as we go. So if you take a look, next slide, these are the burr areas that we're talking about. And also maybe take a look at the shiny or the burnished area. Mainly we're calling that a shear band that's created. And also that angle of fracture, or fracture angle as it's labeled on this drawing, that has some direct relationship to the die clearance being used and ultimately how much burr is being created. So this is what we're trying to control and at least trying to minimize. So the slug as it pops through, you can see the burr on the slug. It's kind of a mirror image. The slug on the, or the burr on the slug is on the top part of that. And of course the burr on the punched hole is on the bottom of the sheet. So next, definition of a burr. I'm not going to read through all this, but basically it's that protrusion or that raised edge on the material after that modification, in our case, a punched hole. And then burr height. It's defined as the maximum distance the burr projects above that surface. You take a look at this, we're talking about that punched hole again, and that burr off the bottom surface is a certain height, again, as a result of the clearance being used and the material type and thickness being punched. So basically, now we're standards does your company use for manufacturing? And basically, here's your choices. An ANSI standard, American National Standards Institute, has some recommendations on burr and burr height. Something your customers are recommending or specifying, maybe you see this on your part prints and you're responding and trying to accommodate that. Or something else, something within your own company perhaps. Or maybe none of the above. Maybe you just run through the normal processes in your fabrication and basically get what you get and move it through that manufacturing process. And your particular case with your parts, not a big deal. So we're going to tabulate these. Meanwhile, I guess the burr height, as it relates to most fabricators, a lot of times in medium gauge, meaning 20 to 14 gauge material, your burr heights are less than, say, 10% of material thickness, and that could mean as little as 3 or 4 thousandths of material thickness in terms of burr height. And that, if you think about it, the thickness of a human hair being only about 4 thousandths thick, you're not talking about a real heavy, pronounced burr if you have decent tools, decent machine, and end up with a decent looking hole. But in some cases, it's still too tall, too much burr for what your customer requirements are. So we should be getting close to some of these results now, and it looks like we have them tabulated. Interesting. So about 20% of you use the ANSI standards, about 35% are responding to what your customer requirements are, something on your print relative to the burr. Other listed about 20% of the time, and then basically the remaining numbers about 25% where you don't have or are not following any specific guidelines. So, what is an acceptable burr height? I touched on this a little bit ago. 10% of sheet metal thickness is kind of the age-old standard, and I'm sure I'm sensing a lot of heads shaking and some heads maybe nodding. And the reason for that is this. Basically, in thinner materials, low carbon steel environments, you're talking about a burr thickness then that's, say, 5 thousandths or less in light gauge material. This 10% thickness came from some publications that were done many, many years ago. Currently, today, this 10% burr height is being challenged because if you get, like I mentioned earlier, if you get into that 5 thousandths or greater range, that's where customers typically have a problem with that. They potentially can be sharp enough to either catch someone who is assembling a part, maybe even the workforce at a fabricator, or certainly down the line to your end user. So the idea is to try and minimize this or get rid of it if possible. There are some different materials that produce less burr height depending on the clearance used. And at the tail end of this, you don't have to read all through this right now, but there's an engineering clearance that's basically a result of some research being done in a number of different places. So we're going to get into what we can do now in trying to control or help limit that burr. Some of this is pretty obvious, but there's some components of it that maybe you need to be aware of, or at least be a little bit more vigilant with. One is to check the station alignment, extremely critical. Sharp tools kind of goes without saying, but you would be surprised the number of shops that I have visited that complain about burr issues, and when we go and take a look at the tools, they have some pretty rough looking edges on both the punch or dies. And finally, die clearances, and this is a big part of that as well. So, getting into this a little bit, oops, we have this glaze over warning now. And so, you guys want to maybe stretch or pound your energy drink? Believe me, I won't linger over this topic too long, but I practiced an explanation here. You take a look at this, and basically there are a couple of different benchmark standards that two different entities created, one a German, one a French standard. Basically they're saying this, that you have a benchmark for burr height on a given material thickness based on tensile strength. The thicker the material and also the greater the tensile strength of that material, the less the burr height standard would be a percentage of material thickness. So in other words, the thicker the material, the greater the tensile strength, you're going to be looking at some burr standards that are considerably less than that 10% ratio we've been talking about, maybe as little as 2 or 3%, depending on the clearance used and so forth. So this is the burr height standard relative to material thickness and tensile strength that I mentioned. Just basically kind of a reference point here as we get into some of this discussion on how to get rid of burrs and so forth. So now we're going to move to the regular die clearance chart that you're probably used to seeing. It's a basic chart, probably seen similar charts before. On the left, it's the material type and thickness. And on the right, it's the percentage of material thickness that this chart and Wilson is recommending you use for a die clearance. You can see it's slightly different for blanking versus piercing. The reason for that is we basically want to keep that slug, which is your part in a blanking operation, as flat as possible. So by keeping the clearance a little bit tighter, that actually minimizes that slug from deforming, and you get a little bit flatter slug or part if you are in that blanking operation. Okay, moving on from this. So another poll question here. So what deburring or finishing method are you using with most of your punch parts? In other words, after you've punched your holes and the parts are coming off the turret and you need now to get rid of the burr based on those standards we talked about earlier, what is the most common method for removing? Are you using hand deburr tools, files, bench grinder maybe, DA or other air sanders? Or finishing machines? By this I mean a time saver type machine, tumblers, etc. Or maybe some combination of those two, or maybe something else. So while we're tabulating here, I've done a number of question and answer sessions with customers here the last couple of months on this topic, and there's a number of fairly popular machines out there, and Time Saver is just one brand of them. There are many others, but there's a combination machine that's been out for a while and now being refined a little bit more that basically does the belt sanding and brushing all in one operation. So if you haven't seen these machines, might be worth a look. I would give maybe one small caution, is the replacement on the brushes. Seems to be a fairly expensive replacement process, and in some cases a little bit of heartburn trying to find a source that's fairly affordable as these as the brushes wear out. Okay, I think we're set with the results now. Seems. Okay. 50 or so percent do some sort of hand finishing operation. Just 8% go through some sort of finishing operation only, and then the combination of the two is probably almost as popular. About 41% are doing some sort of combination, meaning A and B. Okay, we're going to move on a little bit and see if we can get rid of some more of that burr with some of these general maintenance procedures. Proper alignment on whether or not that slug determines how much alignment is at an issue here. So what we're talking about here, as I mentioned earlier when we looked at that diagram, is the shear band around the perimeter, in this case looking at a couple of slugs. And it's not so critical, that shear band, that's the shiny area around the perimeter, that's the burnished area, and it's not so critical, I guess, how much of that is shiny and how much is the dull gray or the fractured area, but mainly that it's consistent around the perimeter. That shear band burnished area will change depending on the material type that you're punching. You'll see much more of a shiny band on, say, thinner or softer materials, but stainless steel, you'll see very little of that penetration, which creates the shiny area when you're running stainless or materials with a higher yield strength. But only you want to make sure that around the perimeter of that slug, or in this case of these, on the bottom left here, there's a hole, a little hexagon-shaped hole. You can see the same thing there. You want to make sure it's even around the perimeter. If it's not, or if it tends to go from, say, 10% to 50, 60, 70% on one end of that slug or one side of that part, you've got most likely some sort of an alignment issue. Okay, another alignment problem people run into is a rat tail. And what exactly is a rat tail? Well, that's those little slugs or slivers that extend from one end of that punched part. They're normally seen on slitting tools. This is what they look like. They can be, just a small little piece. They can be long and narrow and extend quite a bit off the end of that slug. Just depends on maybe your overlap. And obviously the hope is that you can try and minimize or get rid of these completely. So the troubleshooting on these is a number of things. Usually it's a combination of some sort of arrangement where your station alignment or the auto index station is not quite correctly aligned. You get into some worn things like maybe the turret or the punch are worn, or the guide keys, maybe the shot pin or pin bushings in your machine have seen their better day. Or this is a big one too, the station might be in pretty good alignment, meaning punch to die is aligned fairly well, but you don't have the machine's X or Y axis squared up to that station. So you've got, say, a rectangular tool that's maybe a couple of degrees, on the dial, maybe at, past 12 o'clock or not quite to 12 o'clock, and they're not squared up. So as that part is being slit across, as the sheet is being moved, you get those stair steps, and that can help create a problem or an issue where you have those rat tails that enter into the picture. Okay, sharpening recommendations. Again, it seems pretty obvious, but I can't tell you the number of accounts. Like I say, I'll stop in, have a look at the tools, and they're in pretty rough shape. Just depends on how often or what you're punching and how often you sharpen the material or the tools themselves. Definitely going to get a better edge quality, more accurate part the sharper you keep the tools. So, basically we tell customers to try and get to those tools once you have a 10,000ths radius on the edge. And what is that? I mean, it's tough to measure that. You can do the proverbial fingernail check, just like you pull a knife out of the drawer in your kitchen and run it on the edge of your fingernail. So if it catches a little bit or scrapes material off your fingernail, you know it's sharp. But if it slides over that fingernail without catching at all, you know you got a dull tool. Some other things, some other warning signs you can take a look at. The burr starts to become excessive, more so than you're used to, and that goes for the bottom of that sheet or the top of the slug if you're pulling a few slugs out of the bin. To take a look at those. The punching noise starts to increase. Dull tools make a whole lot more noise. Other issues, galling problems on the tool, stripping issues would be a sign the tools are starting to wear. Okay, moving on to some other issues that end up being a challenge for fabricators to keep good edge quality. Basically, we're talking about pinch points. What's a pinch point? Well, these are the issues you get from an overlap. And pinch points are areas where the material is being stressed as the punch comes down to make another hit. It's another look at pinch points and what can we do to minimize those or maybe even eliminate them? Well, a couple of things. One, maybe some of you have heard of this, but an oblong or a long D-shaped punch in a rectangle die. We'll go over a little bit more of that in a minute. There's some rolling tools out that can address this, a rolling pincher, or maybe using that rolling pincher on some thicker materials where it's too thick to actually score the material so you can snap it off, but you can pre-score the material and then punch once you're done. Take a look at some operations there. And then the rolling shear. This is a rolling tool that actually cuts right all the way through the material. And again, it eliminates completely the pinch point you get with a parting tool setup. And then finally, running a tool over the top of that edge and helping to minimize the burr and that pinch point. We'll go through some of those in a bit too. First, this oblong or long D-shaped punch. So here's a look at that rectangle punch, rectangle die, and that pinch point. This is some 18 gauge galvanized material, and that's a pretty decent representation of that pinch point that you would get. And again, we're not talking about a burr here so much as just this little mark area where that stress is involved with creating the pinch point. So now if we take that same exact material and the same die and change out the punch and use an oblong punch in that die or maybe that long D punch in the die, this is what we get. So you can see it's considerably better. Maybe doesn't completely eliminate that, but in, I would say, the softer materials, aluminum, copper, etc., you might be seeing as much improvement as 60 to 80% improvement. A mild steel might be more in the order of 40 to 60% improvement. And stainless steel, just because of the way it fractures and stresses a little bit less in those overlap areas, you're probably looking at improvement in that 30 to 50% range. So for those that wonder about using an oblong tool and you're using that rectangular tool to use some sort of a microjoint tab, might be a good time to explore some other microjoint tab options. Or use this long D-shaped tool where you can use that in an auto index station and rotate that tool to the square end and use that to produce your microjoint tab. Some other pinch point pictures on the left, you see rectangle punch, rectangle die. This is just some straight mild steel, and you can see the improvement with the oblong punch and the rectangle die in the picture on the right. Okay, now we're going to take a look at some wheel technology options. First one we're going to talk about is the rolling pincher. And this is a tool that creates a little score mark on the top and bottom of the sheet. If you take a look at this little depiction here, you can see that that scoring is fairly significant where you want to actually snap the part free once the scoring or pinching operation is completed. And this particular tool is generally acceptable to run in materials that are in that 20 to 14 gauge mild steel and aluminum range. Probably 16 gauge stainless steel would be the maximum. So this is lighter or light to medium gauge material where this solution might be an option. Here's a top view of what that scoring might look like on a piece of, I believe this is some 18 gauge. So you can score and use this tool right up to some pre-punched holes. Let's use it in some sort of combination. but they definitely work better on a square or rectangular part geometry. Probably not a great solution for parts that have any sort of contour or radius features to them. Okay, another way to use that rolling pincher is to actually, in the thicker materials, again, heavier than, say, 14 and 16 gauge, but you can score the material before punching, probably not quite as deep, much shallower pass than when you're pinching to try and break the parts out free. Maybe 10 or 15% of material thickness on top and bottom would be enough. And then you actually use your normal parting tool or slitting tool to go right over the top of that edge and punch it. And here's an example of what that edge might look like and the improvement with it. So you can get quite a bit of improvement. Seems to work really well on say, some thicker aluminums where that pincher mark is pretty severe. So that pre-score and then post-punch combination works pretty well to clean those edges up. Okay, next we're going to talk about some of the things you can do to help get rid of or minimize the scallop you might get in punching out some larger diameters, either some large holes on the middle of a sheet where you can see there's some pretty significant scallop on this particular picture. And likewise, it's not a very good picture, sorry about that, but on the right there's some scallop marks. We'll take a look at a video here in just a second, but this is the rolling shear wheel tool. And this one is designed to cut through the material completely. And again, this is typically some lighter and medium gauge materials where this comes in as a suitable application. And again, we're talking about 20 to 14 gauge for the most part, 16 gauge stainless steel. And again, especially even with lasers out there, if you have some formed features on your parts that you're running and don't want to have to get a better edge, don't want to have to, take them off the turret and set up and somehow try and orient on your laser, you can run a rolling shear tool. They work great for these contoured edges or cutting out large diameters. We'll take a look at this video now, and you'll see at first that same hole feature being punched out and nibbled out, leaving those scallop marks we talked about, and obviously taking a whole lot more time. And then we'll see what that rolling shear does with that same size hole. Okay, so just to touch on wheel tool solutions, the rolling wheel family has been around now close to 20 years. Wheel tools run on most hydraulic and most all servo-electric machines. They will not run on the older mechanical ram machines, but it's a nice tooling solution. Again, it probably eliminates all of the scallop and any of those pinch point marks that we were talking about. I would say it doesn't give you a completely burr-free edge if you're running the rolling shear. It gives you a pretty nice edge, similar to what you would get on a punched hole, where you're using the proper die clearance on the station that's been aligned. It's a minimal amount of burr, but definitely does eliminate the nibble marks, the pinch points and certainly is a whole lot quicker than nibbling out large diameters or contours. Okay, so the next thing we're going to take a look at, is a Deburr application. And these are tools that, let's say you have done everything possible to try and minimize that burr. You've got good alignment, your tools are sharp, you're using the proper die clearance, and you still have an edge or a burr on your, at least hole features, or maybe on the perimeter of your part. Your customer just can't accept that. So you can do some things. Even if you have a mechanical round machine, there is an option on a Deburr tool. We'll run this little video. There's no sound on this one, so I might just talk through this thing a little bit. But it's basically a coining tool, and you can see it sort of coining and putting a little bit of a chamfered edge on that burr as you nibble it across. And we're slowing this way down. They don't have to run at this speed, of course. But that's an option, fairly affordable option. I think this tool is $600–700, something like that. And if you had maybe one edge on a hole or an opening that needed to have that chamfer to it, it might be a good solution. Okay. Next, we're going to move away from this one and take a look at a different Deburr tool for the more modern machines. This is basically the ball bearing style tool system. And this would need or require a hydraulic or a servo-electric punch press to be able to keep the ram or the striker down on top of the tool while it runs. And you can see some of the features here. It'll handle quite a variety of material thickness, all the way from as little as a 30 thou thick material, all the way up to 200 thousandths thick. The tool is adjustable in terms of spring tension. Basically, you adjust that depending on the burr thickness of the material. So we'll have a look at what this tool does now. Well, I'm sorry, this one is silent. I was just informed. So it's showing a little bit of a chamfer feature right now, kind of an animation. And then it's going to zero in, I believe, on some parts there we go. So it's doing the entire perimeter of this part. But you can see, if you had a fairly good sized part and plenty of hole features, and you had to go through each and all the hole features as well as the outside geometry of the part, you're talking about some additional cycle time, even as quick as this is. So my experience with these Deburr tools is some customers will have an opening, say like this large one it's doing the perimeter of right now, where that's the key feature their customers need to have Deburr free, or at least have that slight chamfer put on that edge. Obviously this video is kind of showing you doing the whole entire part here, but fairly affordable tools, fairly easy to program. The little bearings are replaceable. Eventually they will probably wear out. You'll need to replace those. And they're great, like I say, for eliminating that secondary operation, so you don't have to pull those parts out of the machine and run them through a whole other process. Okay, so basically coming to an end of this presentation, there's no great mystery to getting better edge quality. 75% of it basically can be attributed to either good alignment or improving the alignment of the machine, sharp tools, and proper die clearance. In some cases, an older machine is just going to get you so far. You just have too much play between the tool and a little slop in that station, either holding the tool or some travel on that X or Y axis that just doesn't give you perfect alignment to give you that minimal burr that might be acceptable. But 25% of it might be a tooling solution where either a specialty tool like we talked about might be a good solution, or some sort of post-punching cleanup tool, I would call it, like the Deburr tools we've been talking about.